Hello, welcome to this video where we discuss some extra problems on the Thevenin and Norton analysis. And as I explained in class several times, many of the applications like first order circuit analysis and even AC analysis are all based on Thevenin and Norton. So it's very important to be very fluent in them and how to build these equivalent circuits. Okay, let's take a look at some examples. Okay, we have first this example here. We have a circuit. It has a number of components. We have actually three independent sources, and we have one dependent source. And our target is to find the voltage V naught at the output using Thevenin equivalent. Okay, so what's happening here? When this is used, I usually take this as my load and I build a Thevenin equivalent seen from this side. Okay, so I'm not gonna be including this resistance here to this side. So I will find R Thevenin looking from this side here. So I need V Thevenin and I need R Thevenin. So don't make the mistake of including this load resistance in your Thevenin. This one's going to be connected to your load analysis. Of course, removing one resistance also will make your circuit a little bit simpler. So just remember this will be our Thevenin analysis here, looking from these two terminals into the circuit. To get Thevenin analysis or to get Thevenin equivalent, we have to calculate V Thevenin and R Thevenin. And I'll show in the next slide how this is done, just to remind you of how we did it in the past. Okay, so for Thevenin, we replace the whole circuit connected to the source, to the load that we have, the 1 kilo ohm that we have, with V Thevenin and R Thevenin. If you want to get V Thevenin, what you do, you create an open circuit between these two terminals. So get rid of this 1K, get rid of it, and if you have an open circuit, then there is no current flowing in this equivalent circuit, and the voltage you're going to be measuring here is V Thevenin. So V Thevenin is obtained through only one approach. You create an open circuit, get rid of your load resistance, keep this two terminals open circuit, and calculate this open circuit voltage, and this will be your Thevenin equivalent voltage. To find R Thevenin, there are two ways. The first one, and the book uses this sometimes, is that they simply create a short circuit. You say, well, why don't you put a short circuit here? So they short the output, so this becomes a short circuit. And then if you have a short circuit, you can see the current flowing in this short circuit is V Thevenin over R Thevenin, because you don't have any other loop. And if you already calculated the open circuit voltage V Thevenin, you can simply say that R Thevenin is V open circuit of I short circuit. This one way of doing it. Another approach which I personally prefer is to get rid of the Thevenin source, okay? And this Thevenin source, as I explained before in class, represents all the independent sources that you have in your circuit. So if there are no independent sources, this term will be equal to 0. So you go back to your original circuit, remove all the independent sources, make a voltage source a short circuit, make a current source an open circuit, and then the circuit, effectively the equivalent circuit, becomes something like this. It's simply R Thevenin. Okay, let me just erase this one. It simply becomes something like this. It's simply R Thevenin. Okay, so if you have R Thevenin here, what I do, if you can find the input resistance looking between these two terminals, the same terminals we used before, so these two terminals here, after you get rid of all the independent sources, with short circuit now, or it's not there, then the input resistance are Thevenin. But if you have dependent sources, this is when you have to put an external source. I usually put an external source of 1 volt, okay? This is an external, and then I try to find the current drawn from this source, which I call I external. And the ratio between this external voltage of 1 volt and this I external will give me the Thevenin resistance. Okay, let's see how this is being applied, but let's first get the Thevenin voltage. So as you could see, I created an open circuit at the input. I created at the output of the circuit. So I got rid of the 1 kilo ohm. I got rid of the 1 kilo ohm here, and I have this part is really hanging in the air, so there is no current flowing here. And now what remains is to find this V open circuit. Okay, if to be able to find this V open circuit, I have to find the currents or voltages in the circuit. As you can see, I have to use loop analysis or nodal analysis or superposition or any other technique that you may want to use. I calculated the number of nodes. I found that I have 1, 2, 3, 4 nodes in addition to ground. I have how many loops? 1, 2, 3, 4 loops. I decided to go for loop analysis. Okay, and I would decide now to simplify things a little bit. I can see from this one that I1 is equal to 4 milliampere just by inspection here, because I have this current source 4 milliampere. And I also have that this 2 milliampere it is joined between loop 1 and loop 2. This 2 milliampere is equal to I1 minus I2. So this is the second equation I have. So already have I1, then I can get I2 is also 2 milliampere. So already calculated I1 and I2, just very simple. I now have to solve only for I3 and I4 by writing KVL in these loops. Okay. So we go to loop 3, we start to write KVL. I go in the clockwise direction, and as I said in class, I usually take my drops to be positive in the direction of the current of the loop. So it's going to be positive, negative, positive, negative, positive, negative. Okay, so I go now this way in this direction. So this is going to be minus 1k I3 minus I2. This drop here is minus 1k I3 minus I2, minus 1k I3 minus I4, minus 1k I3 is equal to 0. And this is what I have here. Okay, you know what's I2? Get rid of I2, replace it by 2 milliampere. You will have only one equation between I3 and I4. I'm not showing the simplification steps. I did them on an external piece of paper. If you want to do them, this is fine. Take a piece of paper and do them and see that you collect all the coefficients of I3 and I4. But this is the equation I got for I3 and I4. I need one more equation for I3 and I4. Then I have to apply loop analysis in the fourth loop. Okay, and the fourth loop there should be no problem because I have only voltage sources. As you can see, this is a voltage controlled voltage source and this is an independent voltage source. So again, we're going to go this way and then we'll sum all the drops. And if you remember, I take the drops to be positive in the direction of the current. So this will be minus 1k I4 minus I3. This is minus 12. This is minus 1k I4 minus I1 plus 2Vx is equal to 0. Remember, Vx is a controlling parameter. We have to get rid of Vx. We have to write it in terms of the unknowns we are solving for. This is Vx here, okay? And this Vx is nothing but 1 kilo ohm I2 minus I3. And observe the polarity. This is positive, negative. So this drop is 1 kilo ohm I2 minus I3. So we write KVL for the last loop and then we write the fourth equation. We already calculated I1 and I2 from the first and second equations. Now we have to solve I3, third and fourth equations for I3 and I4. So I went around this loop, as I said. I summed the drops. So this is 2Vx minus 1k I4 minus I3 minus 12 volts minus 1k I4 minus I1 is equal to 0. I know what's I1, it's 2 milliampere. I'm going to replace Vx by 1k multiplying I2 minus I3. If you collect all the coefficients, you see that this is the equation you're going to be getting between I3 and I4. So now I have two equations I can solve for I3 and I4. And if you do that using your calculator or using substitution or Gauss elimination or whatever, you get the answer I'm going to show you in the next slide. So we did the solution, and surprisingly we got I3 equal to 0 milliampere. And don't get confused, sometimes the circuit will organize itself to give you an answer of 0. Okay, now I need actually only I3 to get the open circuit. Why? Because if you see here, if I consider this one to be point A and this point B, I'm looking for VAB. And I obtain VAB by drawing a contour that's connecting A and B, and the shortest contour is this one. Okay, of course, if you have 45 minutes to spend in this part. You can go all the way around, and some all the drops, whatever. There are many tricks you can do, okay? But I don't recommend you take the shortest path just to save yourself some time. You'll see that I have only to add two drops. So the first drop is this one, positive, negative, and this drop, positive, negative. Okay? So in moving from here to here, I will say that VEB is equal to this drop plus this drop. This drop here is 1K multiplying I3, and this drop here is 0 because there is no current flowing here. And because I3 is 0, I know that V Thevenin, which is V open circuit, will be equal to 0. This drop is 0 and this drop is 0. Then there is no V Thevenin. We had a similar example in class where we got V Thevenin equal to 0. So these independent sources, their values resulted in no current flowing here, and meaning there is be no current flowing in the load as well. So this means that Thevenin voltage is 0. One other situation where you can get a zero Thevenin voltage or a zero Norton current when you don't have any independent sources. So if I give you a circuit with no independent sources, and then I ask you find Thevenin, you immediately should tell me Thevenin is equal to 0 because there aren't any independent sources. Independent sources are the ones that give energy. Okay, and the rest, this is not really a true source. This is simply another component that enforces one more relationship between the voltage and the current, or the voltage and the voltage between these two terminals and the voltage between these two terminals. But this one does not supply energy. So if I didn't have this one, didn't have this one, there's no Thevenin. So just remember, for circuits that do not have any independent sources, Thevenin is equal to 0 and the I Norton are equal to 0. Okay? Okay, so now we go to part 2. Part 2 is simply to replace the circuit, try to calculate the Thevenin resistance. Okay, so calculating the Thevenin resistance means that you get rid of all the independent sources, okay? And then, and this is what I did. So I removed all the current sources, they are open circuit. I removed all the voltage sources, they are short circuit, okay? And then I applied an external source, and you can see this is the external source I connected in place of the load. This is of 1 volt, and my target is to find the ratio between this 1 volt and the external source. Okay, so I recommend that you draw the circuit yourself and replace every current source by an open circuit, every voltage source by a short circuit. So when you do that, the circuit, the equivalent circuit between these two terminals will have only R Thevenin. Okay, because I got rid of V Thevenin. There aren't any independent sources anymore. Okay, so I redrew the circuit, and this is what I end up having. This circuit has two nodes, 1, 2, in addition to ground. It has 1, 2, 3 loops. So I prefer to use nodal analysis here because I have only two nodes. At node number 1, let's apply KCL. So you get V1 over 1K, this is the current flowing out here. V1 minus V2 over 1K, this is the current flowing out here. V1 plus 2Vx minus V2 over 1K, this is the current flowing out here. Okay, notice if you have something like this, then the total voltage drop across the 1K, it is V1 plus 2Vx minus V1, and this divided by 1K. So what I did at node number 1 is that I summed all the currents flowing out. I set them equal to 0. I got this equation here. You have to get rid of the independent of the controlling parameter of any source, of any dependent source, as we explained earlier. So this Vx is this one here after you simplify the circuit, but this Vx is nothing but V1. So replace every Vx by V1 and multiply both sides by 1K. Collect all the coefficients. You will end up with this relationship governing V1 and V2. V1 is 2 over 5, 2/5 of V2. Okay, now let's apply KCL here. We have how many currents flowing out from this node? 1, 2, 3, and 4. Okay, someone may say, well, we have voltage sources, I may not be able to write the currents. No, you should be able to, because you have series resistances with these sources, and this should cause a problem. These sources are benign sources. Every time you see a voltage source with a resistance in series, this means you can apply KCL without a problem. So this current flowing out here is V2 over 1K. This current flowing out here, V2 minus V1 over 1K. This current flowing out here is V2 minus 2Vx minus V1 over 1K. This current flowing out here is V2 minus 1 divided by 1K. Notice that I gave a value for the external voltage. Sometimes I can get away for simpler circuits by keeping it as a symbol. But for a practical circuit like this one, I have to give it a value of 1 volt. It doesn't matter, make it 1 volt or 5 volt, it doesn't matter. If I make it 1 volt, then R Thevenin is 1 over I external. If I make it 5 volts, then I external will be scaled up 5 times. Then again, R Thevenin will be 5 volts over I external. Okay? Now, this is the second nodal analysis I wrote. Again, get rid of Vx. Vx is equal to V1. If you organize everything, get this equation: 4V2 minus 4V1 is equal to 1. So now we have two equations and two unknowns, V1 and V2. I can solve them and get V1 and V2. If you did this solution, you'll get that V2 is equal to 5 over 12 volts. I really need only V2 to be able to calculate the external current, the current being drawn from this external 1 volt source. If this is 5 over 12 and this 1 volt, then the current flowing here is 1 minus 5 over 12 divided by 1K. This will give you 7 over 12 milliampere. Then the Thevenin resistance seen by this circuit is 1 volt divided by 7 over 12 milliampere. So this water right here is V external over I external. Remember, if you take this one as 5 volt, you will see that this one will be scaled up 5 times. So the ratio will be the same. I take it here as 1 volt. So 1 over I external. So 1 over 7 over 12 milliampere. Okay? And this will give me 12 over 7 kilo ohm. So I could have stopped in the after I learned that V Thevenin is equal to 0, because if V Thevenin is equal to 0, this means that the output voltage across the load is equal to 0. But I continued anyway to show you how to calculate the Thevenin resistance as well. Okay, so this is really how the circuit looks like. 0 voltage in series 12 over K, 12 over 7 kilo ohm, in series 1 kilo ohm, which is our load. Okay, let's take a look at one more example. We have this circuit here and would like to apply Norton theorem to find the maximum power that can be delivered to this load resistor. So this load resistor is not given a value, but we know from a maximum power transfer theorem that this load resistor should be equal to the Thevenin resistance, which is equal to the Norton resistance, in order to get maximum power transferred from the circuit to this load. Okay, so what you have to do here, you have to find the Thevenin equivalent, not the Thevenin, the Norton equivalent between these two terminals, or the Norton equivalent between the terminals of RL. So RL will not be a part of this circuit. Okay, and once we found this Norton, we can simply say that RL should be equal to the Norton resistance, and we can calculate from the Norton current, the Norton resistance, and RL, we can calculate the maximum power being delivered. Okay, so what we did here, what we're going to do, we're going to replace the whole circuit by an equivalent. This is our circuit. It's a big box. I'm not showing it all here. I'm just showing the equivalent circuits. This I Norton, this R Norton, and this RL. And to find the iron Norton, the book recommends and the way you should do it is that you create a short circuit. So get rid of RL, create a short circuit, and the I short circuit will give us the current flowing, and this current flowing here will be equal to I Norton, because once you short this part, you bypass the Norton resistance. Now, how to find R Norton? There are again several ways of doing it. One way is to create an open circuit. One way, which is fine, is to create an open circuit, get rid of RL and create an open circuit. So this is now how the circuit looks like. So this is R Norton, I Norton, okay? And you can see that the open circuit voltage you're going to be measuring, which is this one here, is I Norton multiplying R Norton. So if you know I Norton already, you can get R Norton. Okay? The way I prefer to do it is a little bit different. I prefer to get rid of I Norton completely. Remember that the Norton current represents all your independent sources. So I go and remove all the independent sources. I make all voltage sources short circuit or current sources open circuit. This simplifies the circuit a lot, and I put an external source. So what I do is that I draw it that way. I keep only the Norton. I keep only the Norton resistance. Okay, this is our Norton, and I put an external voltage source, and then I try to find the ratio. I try to find the current being drawn from that external source, and this will give me the Norton resistance. So let's now first get the Norton current, and to get the Norton current, what I'm going to be doing, I'm going to be removing RL, and I'm going to be shorting the output. So this is where RL was. I create a short circuit here, and this is my circuit. My target is to find I short circuit. So you have a circuit, and you want to find the current I short circuit. So you have to solve the circuit using loop analysis, nodal analysis, superposition, whatever. I have how many loops? I have 1, 2, 3, 4. I have how many nodes? I have one node. These two are one node, and they have a second node. So nodal analysis here is way simpler than loop analysis. So I'm gonna go ahead and use nodal analysis. I have only the voltages V1 and V2. Remember, this is all one node. So let's apply KCL here. The sum of all currents flowing out from here are equal to 0. This is how I like to write it. So minus 1 milliampere minus Vx over 2k plus V1 minus V2 over 4k plus V1 minus V2 over 2k is equal to 0. Okay, this is the expression I wrote. You have to get rid of Vx. Vx is this controlling voltage, which we have from our original circuit, but Vx here is nothing but V2. So every time I'm going to see Vx, I'm going to replace it by V2, multiply both sides by 4k, then this minus 1 milliampere becomes minus 4 volt, minus 4 volts, move it to the other side, becomes 4, collect all the terms, you obtain this equation here. 3v1 minus 5v2 is equal to 4. Now we go to node number 2 and then we apply KCL. So the sum of all currents flowing out are equal to 0. Remember, this is a current flowing out, this is a current flowing out, this is a current flowing out, this is a current flowing out. Remember, these two are the same node. So we have 1, 2, 3, and 4. Okay, then V2 over 2k plus V2 over 2k plus V2 minus V1 over 4k, which is this current flowing out, plus V2 minus V1 over 2k is equal to 0. Okay, so I combine these two terms and I wrote them as 2 V2 over 2k. Okay, and the others are still there. Multiply both sides by 4k, collect all the terms, you obtain this equation here. Solve equation number 1 and equation number 2. You'll get that V1 is equal to 2 volts and V2 is equal to 14 over 3 volts. Now remember that my target is to get I short circuit, but this I short circuit here is equal to this current plus this current. So I short circuit is equal to V2 over 2k plus V2 minus V1 over 2k. So once I have V1 and V2, I know what's I short circuit. So this is what I did here. I got I short circuit is equal to V2 over 2k plus V2 minus V1 over 2k. This current here is equal to this one plus this one. I already know what's V2. I know what's V2, it's 2 volt. I know what's V1 is 14 over 3. You put all this and you simplify. This will give you 1 milliampere. This will give you this becomes 6 minus 14 will give you minus 8 over 3 divided by 2 minus 4. So we get minus 1 over 3 milliampere. So I short circuit is minus 1 over 3 milliampere. So what does the negative sign say here? Is the negative sign simply saying that the Norton equivalent circuit is trying to push current actually from this side to this side. It's the Norton current is 1 over 3 milliampere, but it's trying to push current in your load from here to here. Okay, so it is opposite to the assumed direction. Okay, very important to remember that. This is the meaning of this negative sign. Now the second part we would like to do, I'm gonna get rid of this short circuit. and put an external source here, okay, I will make this one open circuit because this is the only independent source I have. And so the circuit will simplify a lot. I have only one source here, and I would like to get the ratio between this 1 volt source, which I'm going to be getting, and the current drawn from it, because this will give me the Norton resistance. So this slide summarizes what I want to do. I'm going to get rid of this independent current source. If I get rid of this independent current source and make it open circuit, then I got rid of the Norton current. Then between here and here, I'm going to see only the Norton resistance. So I'm going to connect an external source between these two terminals, V external, and I'm going to calculate the ratio V external to I external. Okay, so this is how the circuit has been drawn after I got rid of the independent sources and after I put a 1 volt external source. Remember, my target is find the ratio between this 1 volt and I external. This is a circuit like any of the circuits we dealt with in this course. We have how many loops? A loop, a second, a third. We have how many nodes? A node, a second, a third. I prefer to use nodal analysis here. So let's apply KCL here. The sum of all currents flowing out from this node Z are equal to 0. Some of them are equal to 0. So this one here will give me minus Vx over 2k because this one is flowing in. This one is V1 minus V2 over 4k. This one is V1 minus V3 over 2k is equal to 0. So I wrote them here. Remember, we have to get rid of all the controlling parameters. Vx is this voltage, but Vx is really the voltage V3. So every time you see Vx replaced by V3, and multiply both sides by 4k and the collective coefficients, you end up by this expression here, or this equation. I'm not showing the simplification steps. You can do them in an external piece of paper. Now, if you want to write KCL here at this node or here, you'll face difficulty. Why? Because these two are connected by a voltage source. And when you have something like this, we agreed in nodal analysis, it's gonna ruin KCL here and here, and you have to get two other equations. The first equation is that V2 is equal to V3 plus 1 volt, which is this one. Okay, because of this 1 volt battery, V2 is equal to V3 plus 1 volt, or if I organize it, it is 0 V1 plus V2 minus V3 is equal to 1. So this is the second equation. I need one more equation. The other equation, I'm going to get it by using a super node. So I'm going to put a super node here around this source. This is how we handle voltage sources that connect two nodes and there aren't any resistances. Okay, so how many currents are flowing out from this super node? We have 1, 2, 3, and 4. This one is V2 minus V1 over 4k. This one is V2 over 2k. This one is V3 over 2k. This one is V3 minus V1 over 2k. And this is what I wrote here. And the sum of all these four currents equal to 0. Multiply both sides by 4k and collect the different coefficients. You obtain the third equation. So you have three equations and three unknowns, V1, V2, and V3. You solve them using calculator. You have all the voltages you are looking for. I used my computer to do this solution. I got this answer. V1 is minus 4 over 3 volts. V2 is equal to 0 volts. And V3 is equal to minus 1 volt. So don't get confused. You get zeros. This is fine. The circuits can sometimes force these conditions. Remember that my target is to get I external. Okay, but this I external is nothing but the sum of this current plus this current. So you see this current here, which is drawn from the external source, is this current plus this current. This current here is V2 minus V1 over 4k. This current here is V2 over 2k. I know that V2 is 0, so your answer will be minus V1 over 4k, and V1 is minus 4 over 3. So you get 4 over 3 divided by 4k, you get 1 over 3 milliampere. So I bought a 1 volt battery. I was able to show that 1 over 1/3 milliampere will be drawn out of it. Then the resistance seen by this source is V external over I external is 1 over 1 over 3 milliampere. It is 3 kilo ohm. So then the Norton resistance is 3 kilo ohm here. So now I know what is the Norton resistance. I know what is the Norton current. This minus 1 over 3 milliampere. So what will be the value of RL for maximum power transfer? RL will be equal to the Norton resistance, which is the same as the Thevenin resistance, 3 kilo ohm. What is the value of this maximum power? If you have this source, one half of it will go through the Norton, half of it will go through the load. So the current going here will be minus 1 over 6 milliampere. So if you want to get the power, it's minus 1 over 6 milliampere squared multiplying by RL. But remember, RL for maximum power transfer will be 3 kilo ohm. So this is what I have here, and this will give you 1 over 12 milliwatts. This is the maximum power that you can deliver to the load resistor. Okay, we move to show one last example. I would like you to apply Norton theorem to find the voltage V naught. This circuit has two independent sources and have one dependent sources. This is a voltage controlled current source, and it's controlled by this voltage here. Okay, so we're gonna do it exactly like the previous example. We're gonna first create a short circuit here. Okay, and this will give us our Norton, and then I'm gonna remove my independent sources and put an external source and try to find the Norton resistance. So as you can see, I create the short circuit here, and now I have this circuit like any circuit I had before in the course. Would like to solve it. I have 1, 2, 3, 4 nodes. I have 1, 2, 3, 4 loops, but I have many current sources, so maybe I can get rid of some of them. So I use loop analysis. As you can see, I can do lots of simplifications because the current flowing here, for example, I3 is equal to minus 4 milliampere. So I already got rid of one of the unknowns. The current I1 here is equal to 2, it's the same as this current, which is 2Vx over 1K. But what is Vx? You have to get rid of Vx and write it in terms of your currents, because you are doing loop analysis. This Vx here, as you can see, it is this drop. It's gonna, because I4 is flowing in the clockwise direction, so Vx is minus 1K multiplying I4, or 1K multiplying minus I4. So every time you see Vx in this analysis, replace Vx by minus 1K multiplying I4, and this is what I did here. So I1 is 2Vx over 1K, remove Vx, put it as minus 1K multiplying I4, you obtain another equation that I1 is minus 2I4. I have now a first equation, now I got a second equation. The third equation I have to consider this loop and this loop. I have a problem. I can't apply KVL here or KVL here, because you can't apply KVL in a loop that has a current source. So what you have to do, you have to write two other equations, because KVL is ruined here and ruined here. Okay, so what you have to do, you have to use the other equations. First one is that this current here is equal to I2 minus I4. So I have now that I2 minus I4 is equal to 1 milliampere. So this is my third equation. The fourth equation, I'm going to be getting it by building a super loop. So I'm going to use this super loop. I'm going to bypass this current source, and then I'm going to sum the drops. Okay, I have a number of drops, 1, 2, 3, 4, 5. I'm going to sum them. So I will, this one here will be minus 1K multiplying I4 minus I3. This one here will be minus 1K multiplying I2 minus I1. This one here will be minus 2K multiplying I2. This one here will be minus 1K multiplying I2. This one here will be minus 1K multiplying I4, and the sum of all these are equal to 0. Remember, if you have the current flowing this way, maybe talk about I2, if you have a I2 flowing in the way shown, it's flowing this way, then it's creating this drop. And if it's created this drop and I'm counting the voltages in the clockwise direction, this will be included as a negative drop. So the drops I use in this expression is this one, this one, this one, and this one. So all of them are negative. Okay, so let me go over them one more time. This drop here is minus 1K I4 minus I3. This drop here is minus 1K I2 minus I1. This drop here is minus 1K minus 2K multiplying I2. This drop here is minus 1K multiplying I2. Remember, I'm going this way. This drop here is minus 1K multiplying I4. All sum of all of them are equal to 0. Now get rid of the terms that you know. I know, for example, that I3 is 4 milliampere. And then write the equation that you have. You get the fourth equation you're looking for. If I excuse me, if I write this equation, I have the fourth equation. If I put all equations in a matrix form, and I encourage you to do so, this is the one I got. I solved it using, of course, you could use substitution or you simplify them because you already know what's I3. You can do that as well. So you know some of these currents. Anyway, so I solved that system of equations, and this is the answer I got. I1 is 2 milliampere, I2 is 0, I3 is minus 4 milliampere, I4 is minus 1 milliampere. So remember that the short circuit current we're looking for was the current in the fourth loop. Okay, so this short circuit current is I Norton is I4. Go back and check the previous slide and you'll see this indeed the case. So I'm looking for I4 and I4 is minus 1 milliampere. Okay, so now I know what's I Norton. The last thing I want to do here, I'm gonna find R Norton by putting an external source between the load, and I'm gonna make this one open circuit, and I'm gonna make this one open circuit. Okay, so if you make this one open circuit and this one open circuit, and you put a 1 volt between here and between axle load, the load is gone, and I put the source. This is what you end up having. Okay, so this is a circuit, and as I said, sometimes I was able, as I explained in class, to keep this one as a symbol, as a V external. But if you want to use loop and nodal analysis, give it any value like 1 volt. The answer I'm looking for R Norton is 1 volt over I external. So this is a circuit. It has 2 loops. It has 2 nodes in addition to ground. Use whatever technique you like. But the most important thing that I warn you against, because you need to calculate Vx. Vx is your controlling parameter, and Vx is the voltage across the 1K. The total voltage around this loop is V2 plus 1 volt minus V1. So the voltage difference between, if you go all around, the voltage difference that this resistance seen, this 1, 2, 3, 4 resistance seen, is V2 plus 1 minus V1. So Vx will take 1/5 of that, because you have, this is 1K, but the total resistances are 1K, 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 and 2K. Okay, this one is not included. This one is not included because I'm measuring the voltage between this point and ground. This is V2, and the voltage between this point and ground is V1. Okay, so remember, Vx is the voltage across this 1K, and this Vx here is 1K over 1K plus 1K plus 1K plus 2K. So we're 5K multiplying V2 plus 1 volt minus V1. This is the most important thing, and you can get this expression by writing KVL. And this is what I did. Write KVL around this loop here, and again, don't include this one. Go all the way from ground, take V1, go all the way, and then come back to V2. This one is not with us. This resistance is not with us, okay? Now, I use nodal analysis here, so the sum of the currents flowing out from node 1 are equal to 0. So this one is minus 2 Vx over 1K. This one is V1 minus V2 over 1K. This one is V1 minus 1 volt minus V2 divided by 5K. Okay? This is what you have here, and again, get rid of Vx, replace it by in terms of V1 and V2, and multiply both sides by 5K, collect the different coefficients, you obtain the first equation. So I did that, and I obtained this equation: 8V1 minus 8V2 is equal to 3. Now I come to node number 2. The sum of all currents flowing out from node number 2 are equal to 0. This one is V2 over 2K. This one is V2 minus V1 over 1K. This one, if you see the total voltages from here to here, so you get V2 plus V2 plus 1 volt minus V1. So the voltage drop across the 5K is V2 plus 1 minus V1. So the current here is V2 plus 1 minus V1 divided by 5K. So I have these currents. Again, I don't have Vx here in this one, I don't need it. So just multiply both sides by 10k and collect different coefficients, you obtain this second equation. So you have first equation in terms of V1 and V2. I have a second equation in terms of V1 and V2. You solve them for V1 and V2. So I did that and I got V1 equal 0.875. I got V2 equal to 0.5. Remember, my target is to find the external voltage. Sorry, the external current. I need this I external, this current drawn from this external source. This is my target because the ratio between the external voltage, which is 1 volt, to the external current will give me the Norton resistance. So this external current here will be equal to V2 plus 1 minus V1 divided by 5K. I don't want anyone to say that divide by 6K. Why? Because as I said, the voltage between here and here, between here and ground is V2. The voltage between here and ground is V1. Okay? So what I'm doing, I'm going all the way around from here up to here. This is not included. So the voltage drop across this one, this one, this one, and this one, this 5K, is V2 plus 1 volt minus V1. And the current going through is V2 plus 1 volt minus V1 divided by 5K. I already know what is V2, it's 0.5. I already know what's V1, 0.875. If you do this calculation here, you get 0.125 milliampere. It's 1/8 of milliampere. Then Norton resistance is V external of I external. You apply the voltage of 1, you get 0.125. What if you selected this one to be 5? You will see that this one will be multiplied if after you calculate it 5 times the number. So we'll give you 8 kilo ohm. So R Norton is equal to 8 kilo ohm. And the last thing is simply to build the whole circuit with the Norton equivalent. So the last circuit is what we have. We have 8 kilo ohm in parallel with 1 kilo ohm. This is the Norton circuit, and they have Norton current is minus 1 milliampere. Then the output voltage is minus 1 milliampere, multiplying this equivalent resistance, which is 8k in parallel with 1k. So you obtain minus 8/9 volts.